Hello, we will now talk about Chapter 12, Section 2, which deals with chi-squared tests that deal with two-way tables. We got two kinds of tests we're going to deal with. We have the test for homogeneity of populations, and we also have the chi-squared test for association independence. They're really similar tests, and they're done in essence when you see a two-way table information like this. And the key thing to remember is that they have to be categorical variables we're dealing with here. You notice in this particular, and the first problem we're going to have deals with political party affiliation, Republican, Democrat, other, and then gender, male or female. So it can't be quantitative. It can't be quantitative data. The numbers have to be counts in categories. Okay, and so that's the first thing we're going to deal with. Now, in section 1, we dealt with what is known as a goodness of fit test, where we had one categorical variable and we had these hypothesized proportions given to us, and we do a goodness of fit. Does the sample data fit with the hypothesized proportions? All right, but in this case, what we're going to have is we're either going to have two samples that deals with a categorical variable, or we're going to have one sample with two variables. All right, and so it's going to take a little practice as far as determining which tests you're going to do. But a chi-squared test of homogeneity of populations is when you got two populations and you got two samples. And then it asks you to compare the two populations in regard to a categorical variable. So it has, let's say if it's got the people in Madison County compared to the people in, let's say, Limestone County, and it wants to compare some categorical variable. Their religious affiliation or their race or whether or not they've been to college. Okay, but they're comparing two samples, one categorical variable. Whereas the chi-squared test of association independence means you have one sample, but it's comparing two categorical variables. So the way to tell the difference is to most of the time just ask yourself, hey, is it just one sample? And are they asking, is there a difference in the population? The keyword we're looking for is they're going to ask, is there a difference in the population? And the key thing here is, or is it one sample? And it'll say, are these two variables associated? Or are these two variables independent? Or are these two variables related? Or some synonym thereof. Are they correlated? So are the two variables correlated? So something like that. And so in this, by the way, is the Greek letter chi. Okay, so sometimes you'll see it written chi-squared test, and sometimes you'll see it written like that. That is not an X. That is a chi. So that is chi-squared. But once again, it's important that you understand when we do a chi-squared, and that is when we have categorical variables, not quantitative. Categorical. So like in regards to people, it's like what race they are, what state they're born in, the color of their hair, something that categorizes them. Whereas quantitative, if it was quantitative data, it would be like their height, their weight, a test score, the amount of time they spend doing something, some number where everybody pretty much has a different number. Okay. And if it's quantitative, you cannot do chi-squared. So if it's categorical and the numbers are not quantitative, the numbers are counts in categories. Counts in categories. And all of that is sort of an alliteration, right? If you do, in order to do chi-squared, it's got to be categorical, and the numbers are counts in categories. Okay. If the numbers are quantitative, then it's no good. Let's look at a couple of examples. And so is this chi-squared or not? A chi-squared situation or not? So we have nice categorical variables, right? We have is race related to political party affiliation? These numbers are not quantitative. They are counts in categories. This is saying in this group, there's 46 Black Democrats. Okay. It's not like 36. It's not like, that's like a test score or the amount of time doing something. Okay. It's a count in a category. So this would be yes, this is a chi-squared situation. All right. Let's look at this one. So this says the average math grade in each grade and gender are shown. So it's saying like the male freshmen, their average math grade is a 78. For the male sophomores, their average math grade is a 73. This is quantitative data. This number is not a count in a category. This is an average grade 78. It's not like there's 78 male freshmen. That is not a count in a category. So it is no, this is not a chi-squared situation because it's quantitative data. All right, let's look at another one. So for this one, whether or not a tree has a fungus and the type of tree in a particular forest are shown. So you've got oak trees, you got elm trees, you got pine trees, and they either have the fungus or they don't. So you got 42 oak trees that have the fungus. That is a count in a category. It's not like this 42 is the height of one tree or anything like that. It's not quantitative, it's categorical. Yes, the numbers are counts in categories. Let's look at a number. So that one, yes, it is a chi-squared situation. The mean number of leaves for the type of tree in the county the tree is in is shown below. So in Madison County, this is the mean number of leaves. This is quantitative data. This is the mean number of leaves. So this is no, that is not. It's not like there's 1,232 oak trees in Madison County. That's not what that's saying. It's saying this is the average number of leaves. That is quantitative data, not categorical. And so then, all right, here's a tricky one. This is a tricky one, but you can handle it. Okay, the heights of trees in a forest and the type of tree are shown below. So in this one, it's saying, so it lists the heights of the trees categorically. Now, height of tree in general, most of the time you think of quantitative, where every tree's got a different number. But any quantitative data set, it can be listed categorically by putting it in intervals like this. This number, that's not the height of a tree. That is the number of oak trees that are between 0 and 10 feet tall. There's 65 of them. These numbers are counts in categories. There's 78 elm trees that are more than 30 feet tall here. Okay. Yes, this is a chi-squared situation because the numbers are counts in categories. Okay. And so, so with those that we said yes to, we could do the test that I'm fixing to demonstrate to you. We could do a test of homogeneity of populations, and we could do a test of association independence. So let's look at our examples. So a test of homogeneity of populations. So you're going to do this when you have a categorical variable that you're comparing two populations with. You're going to have two different samples. Okay. And you can just call this a test of homogeneity. So let's look and see what this says. It says a researcher wishes to see if there's a difference in the male and female adults in the city in regards to their political party affiliation. She takes a simple random sample of 60 males in the city and finds 40 Republicans, 10 Democrats, and 10 are other political affiliations. She takes another simple random sample of 40 females and finds 10 of them are Republican, 20 are Democrat, and 10 are other. Draw an appropriate graph to compare the males and females, and then perform an appropriate test. All right. Now, first of all, in chapter 1, we did a problem just like this, except we didn't do the test. Okay. Draw a graph of categorical data. And so what we need to do to draw a graph, this is just a little review of chapter 1. First of all, we need to write this as a two-way table. Okay. So we write this as a two-way table. And most of the time, actually, a problem like this, they'll go ahead and give you the two-way table, but I wanted to do one where they didn't. And so you'd say the males, there was a total of 60 males, and we had 40 Republicans, 10 Democrat, and 10 other. And then it said there's 40 females, and then we had 10 Republican, 20 Democrat, and 10 other. In order to make a bar graph, which when you have categorical data, that's the kind of graph you have to draw, we need to find the percents that are in each category, okay? So I need, in essence, the percent of males that are Republican. And so I just said 40 divided by 60, and that's 0.6 repeating. Okay. I need the percent of males that are Democrats. That's 10 divided by 60, which is that. And then 10 divided by 60 is that. For the females, I need the percent that are Republican. 10 divided by 40 is 25%. 20 divided by 40 is 15% or 50%, and so forth. And so then, just like we did in chapter 1, I drew a bar graph where I drew, here's the proportion there. And then, so for the males, they are the blank graph, and for the females, I drew bars up to the with the filled in bars. And then you describe what you see. Now if this was quantitative data, of course we'd cuss. But in chapter 1, you just kind of comment on what you see. And we would say the males in this sample are much more likely to be Republican, okay, while the females are much more likely to be Democratic. And so there you go. So that's what we did in chapter 1. Okay. And we also said, hey, does gender appear to be independent of political party? And we say no here. we would say, hey, just what we said here. No, independence means it doesn't matter whether you pick males or females, you're getting the same percent of political party for each of the parties. And that doesn't happen. There's a difference in this sample because the males are much more likely to be Republican. The females are much more likely to be Democrats in this particular sample. So they're distinctly not independent. Okay, well, now we're going to be a little bit more formal about it. We're, and we're going to come up in essence with a p-value. Okay, so to perform a test, okay, whenever you have categorical data like this, you have a two-way table, you're going to do a chi-square test. Okay, and so the premise of what's being asked here is there, in essence, a difference in the males and females in regards to their political party affiliation. We know it's a difference in the sample, but is it plausible that that difference is due to sampling variability? Or are these samples so different, all right, that it would cause us to say, hey, there appears to be a difference in the males and females for the whole population? There's the name. You can just, so, all right. So for any test, as we've done several times this year, anytime you have to do a test, you have to do 5 things. You have to do 5 things. And this is going to be similar to what we've done before, but we have to tweak it for chi-squared. We have to state the type of inference. We have to state the hypotheses. We've got to check the assumptions or the conditions. We have to do the mechanics, which for a test is test statistic p-value and degrees of freedom. And then we have to do our ending, which is our p-value statement. Now the ending is going to be the same. And a lot of this other stuff is going to be similar. All right, so here's how you do a chi-square test of homogeneity. The first thing is you say, I'm going to do a chi-square test of homogeneity. All right, then your hypotheses. All right, so your null hypothesis is always going to be that there's no difference in the two populations, okay? There is no difference in the males and females in this city in their political party affiliation. The alternative is always going to be that there is a difference, okay? So that's always going to be the null for a test of homogeneity. There is no difference in the two populations in regards to the categorical variable. The alternative is that there is a difference, okay? And so then after we do that, we have to check our assumptions. All right, there's a bit of a tweaking in our assumptions. Of course, we sin. Of course, this is always a condition, and it's always our most important condition. Now, it's 2 samples, so we have to say independent random samples, okay? It says as SRSs were taken, so independent random conditions met. And we've had that condition for several chapters now. Also, the other aspect of the word independence is that our population sizes at least 10 times our sample sizes. So you just multiply your sample sizes by 10. We've had that for several chapters now as well. So there were 60 males and 40 females in our sample. So you multiply by 10. And we say there's got to be, at least that for our sample sizes to be less than 10% of our population size, because we're sampling without replacement here. So we have to have big populations. All right. We do not have normality. Don't in this chapter, because it obeys a chi-square distribution, not a normal distribution. Don't mention the word normal in this chapter. Don't say normal. Don't say normal. So we're not sinning. We are SI, or in this case, ISI, and then, but it's actually easier. That's the good news. All the expected counts have to be bigger than 5. And that's all you have to say. And you have to list the expected counts, and I'm going to show you how we find them in a second. Okay. So that's true for all of your chi-square tests. Okay. For the goodness of fit, for the test of homogeneity populations, for the test of association and independence, all the expected counts had to be greater than 5, and you write what the expected counts are, and I'm fixing to show you how to find them. Okay. Then we do the mechanics. Okay. I'm going to show you how to do the mechanics with your calculator. All right, and then I'm going to show you how to do it by hand. Yes, you have to understand how to do it both ways, okay? But let me show you how to do it with your calculator. So this is what you're going to do. It's a simple little deal, okay? So you're going to be, in essence, given this little matrix here, this 2A table, and we are going to enter it into a matrix. And so here we go. So this is a new thing for us. See the matrix menu right there, right above the X-1, right below the math button? We're going to go there. And so we're going to go second X-1, which is matrix. All right, then we will arrow over to edit, and we are going to edit matrix A. So we hit enter on that. Now, in this case, our matrix has 3 rows and 2 columns. Columns go up and down. Columns are like columns on a building. So this is 3 by 2. So we go 3 by 2. Of course, if you get that wrong, then it's not going to have the correct dimensions, and you'll see it pretty quickly. Then we enter our numbers, 40. And these are our observed counts. Observed counts have to be integers. Okay, frequently the expected counts are, but the observed counts have to be integers or you're going to get an error message. And you just enter your data right like that, 10 and 10. There, I've entered my data into matrix A. All we have to do at this point to get our test statistic p-value degrees of freedom is to do this now. We can do the chi-square test. So we do stat, we go test, and we scroll all the way to chi-square test. There it is. Now, chi-square goodness of fit, that's section 1. This is section 2. So this one works with a list. This one works with a matrix. And so we enter on that. So our observed is in matrix A. Now, let's pretend it didn't say matrix A there. It should say matrix A there. Let's pretend it was blank. That means you need to put matrix A there. And the way you do that is just by going to second matrix and then hit enter on A, and it puts matrix A there. Let's pretend that didn't say matrix B there. So your calculator is going to automatically store, it's going to calculate and store the expected values for you, which is very nice, okay? So you would just go second matrix and go to matrix B, boom, matrix B is there. You do calculate, and that's it. It tells you your test statistic p-value degrees of freedom, okay? And so that is how I got that. Okay, and then I showed the formula. I'm going to talk about that in a second, but all you have to write down is these 3 numbers. All you have to write down is your chi-square test statistic, your degrees of freedom, and your p-value. Now, it is important that you know, degrees of freedom in regards to chi-squared for a goodness of fit is number of categories minus 1. But you have to know this, okay? Degrees of freedom for a two-way table, for a two-way problem is number of rows minus 1 times number of columns minus 1, okay? So in this particular case, we have 3 rows and 2 columns. We've got 3 rows and 2 columns. So 3 minus 1 would be 2, and then 2 columns would be 2 minus 1 would be 1. So this is 2 times 1, which is 2. So that's how that was gotten. And so we have our low p-value. Now, at this point, it's just making your p-value statement, which we've done for several chapters now. The p-value is low, so you reject the hoe. And you have convincing evidence that, and you restate the alternative. So this is just like what we've been doing. This p-value is below 0.05. So I reject the null. There's convincing evidence that, and then you just restate the alternative, that there is a difference. We have convincing evidence that there is a difference in the political party affiliation of the men and women in this city. Okay, that's how you do it now. Okay. Okay, now, by the way, all right, so it's important in your conditions that you list the expected values. Now, how do you get the expected values? Well, if you're using your calculator, the way you get your expected values is it automatically saved it in matrix B. So what you can do is if you go second matrix and then go to the easiest way to look at it is just go to edit matrix B and your calculator automatically put them there. Now, most of the time your expected values are going to have decimals. Don't round them to the nearest integer. In this case, it just happened that they're integers, okay, which is a little unusual. But you have to write down your expected counts there, okay? Or unless they're written someplace else, like if they're written in the problem, in the stem of the problem, you'd say, all the expected counts written above or written in the problem are greater than or equal to 5. All right. Now, how are these now? Okay, so that's how you do the problem. And I don't want to get too technical here, but it's important that you understand what I'm fixing to say as far as how to do this stuff by hand. All right, how would you calculate the chi-square test statistic by hand? Well, you would consult your formula sheet. And on your formula sheet, just like in section 1 of this chapter, the chi-square test statistic is the sum of every observed value minus the expected value squared over the expected value, okay? It is sort of a standardized test statistic similar to this up here, actually. So that's what you do. And you say, okay, well, the observed values, so that's these numbers here. How did they get the expected values? Okay, so our observed values, so here is our two-way table that I wrote out. Okay, all right, so for each cell, the expected values, if you're doing this by hand, and you have to know how to do this by hand, the expected value of each cell is equal to this. is equal to its row total times its column total over the table total. And you have to memorize that formula. Every expected value in a two-way table is the row total times the column total over the table total. What does that mean? Well, it means get your marginal distributions, okay? If you add these up, the total number of males, in other words, the column total for this column is 60. The total number of females is 40. So the table total, the total number in these samples is 100, okay? Now, what about the row totals? Those are the column totals. The row totals, there's a total of 50 Republicans, there's a total of 30 Democrats, and there's a total of 20 other, and so those add up to 100, okay? And so for each cell, like this top cell here, what's its expected value? Well, for the Republican males, so its expected count is going to be its row total 50 times its column total 60 over its table total, which is 100, and that in fact, if you multiply that out, is 30, so this is 30. And so you'd have to do that for every single one of these. So let's do it for the Republican females. What is its expected value? So for the Republican females, you'd say, well, its row total is 50, its column total is 40, and its table total is 100. And so that ends up being 20. Its expected value is 20. And so you would have to do that for each of these cells. But I want you to think about this, and hopefully this will make intuitive sense, okay? So what's the concept of an expected value? An expected value is what would we expect these samples to look like if the null really was true. And in hypothesis testing, the whole logic is we're doing this assuming the null is true. If we look at the sample values and say, hey, if the null is true, what's the probability I get sample values this unusual? Let's assume the null is true. If there really is no difference in the males and females in regards to political party affiliation, what would this look like if we looked at 100 people? Well, when you look at, first of all, the Republicans, when you look at the total, 50% of all the people here are Republican. If there really is no difference in the males and females in political party affiliation, we're expecting both of them to be 50% Republican. So if there is no difference in the males and females, then 50 out of 100, that's 50%. We're expecting 50% of the males to be Republican, so we're expecting 30. And the same with the females. If the females are the same in regards to political party affiliation, we're expecting 50%, 50 out of 100 to be Republican. Well, 50% of 40 is 20. Okay. Then you go on to the Democrats. Well, in the whole group, 30%, 30 out of 100 are Democrats. So we're expecting both the males and the females, if the null is true and there really is no difference, we're expecting 30% of the males to be Democrats. Well, 30% are 60 times 0.3. So we're expecting 18 of the males to be Democrats. And if 30% of the females are Democrats, that'd be 30% of 40. So 40 times 0.3. And so that's 12. That's the expected value is 12. And if you keep going on, we're expecting 20% to be other, and then 20% of that. So that's going to be 12. And then 20% of 40 is 8. Okay. And so those are the expected counts. And so what a chi-squared test statistic is, it's a measurement of how different my sample values are from the expected values, okay? And, but yet it is standardizing it. So if you were doing this by hand, what you would do is you would take your chi-squared formula and you would say, okay, for this cell, its contribution to chi-squared is going to be 40 minus 30 squared over 30, like that. And so for this cell, it would be 10 minus 20 squared over 20, and you would, and then you'd add those up and get your chi-squared. And so then what you would do, all right, if you didn't have a function on a calculator, you'd say, well, how can you get your p-value with that? Well, what you would do is you would go to your table, you go to your last table C with chi-squared, and you would find our degrees of freedom is 2. That tells us which chi-squared distribution we're working with. And so remember, the more degrees of freedom, kind of the less right skewed it is, but all chi-squared distributions are right skewed. And you'd go over and you'd estimate, and ours is 18.05, till you find the one that's closest to 18.05. In this case, it's off of the table. The p-value is going to be this number up here. So in this case, our chi-squared is 18.05, which is greater than that. So our p-value is going to be, in essence, less than that number. And so that's how you do that. Or, as we talked about in the last section, the way you can find a p-value given a chi-squared value is to do chi-squared CDF. And so you would go second distribution, and you would go chi-squared CDF. And with chi-squared, it's always greater than, because chi-squared is always a positive number because it's squared. And so you would go from 18.055555 to infinity like that, and then degrees of freedom 2. And so, and it gives you, and there's our p-value right there. So that's how you find a p-value given a chi-squared. Just go from that number to infinity and put in your degrees of freedom. So and so there you go. And then the last thing is, you know, I would say about it is, you could, if you're doing a follow-up analysis, what you'd have to do, and frequently they would go ahead and give you these numbers. When you found this value and this value, it shows you how much each cell is contributing to the chi-squared. All right, and so if it asks you to do a follow-up analysis, you would just look at each of these numbers, which, like I said, are frequently given to you because it doesn't want you have to do all this arithmetic. And whichever one of these numbers is the biggest is the one that's contributing the most. So to chi-squared. And so there you go. So that's how you do a chi-squared test. Now, a chi-squared test of association and independence is really similar. And like I told y'all before, the biggest difference is just the fact is how the data was collected. In a chi-squared test of homogeneity of populations, you got 2 samples with 1 categorical variable. In a test of association and independence, you're just going to have 1 sample, and it's going to ask, is there a relationship or is there an association between the 2 variables? Whereas a test of homogeneity is going to ask, is there a difference in the populations? So let's look at this one here. So this one here says, an educational administrator wishes to see if there's a relationship between how advanced the student is and his or her opinion about whether or not the school should have stricter discipline policies. He takes a simple random sample of 99 students and gets the results shown below. Perform an appropriate test for the administrator. Well, you notice these are categorical variables. These numbers are not quantitative. They're counts and categories. So the test we're going to do is a chi-square test. And we have a 2A table, and it's just 1 sample. That means a test of association and independence. Okay, so the premise is there some relationship between their level of student and how strict they want the discipline? You know, and so this is what we'll do. First of all, we have, and so we're asked to do a test. We have to do the THAME acronym. So this is called a chi-squared test of association, or you could call it a chi-squared test of independence, either one. Our null hypothesis is always going to be that there is no association, or there's no relationship, or there's no correlation, okay, between the 2 variables. All right. Or the other way of saying this would be that the 2 variables are independent. They have nothing to do with each other. Okay. So there's no association, in essence, between the 2 variables. Okay. Now, the alternative is going to be that there is an association between the 2 variables. Okay, so that's that. Now, and then of course, our assumptions are a very similar thing. All right. It says a random sample is taken, so random conditions met. Don't say independent random because there's just 1 sample. I mean, and that's what we're kind of testing for, is independence here anyway. There must be at least 990 students for our sample size to be less than 10% of our population size. So we've had these conditions for a few chapters now, and all of our expected counts are greater than 5. And how do you could, now, of course, you could do exactly what I did do and do this by hand, but anyway, and so here's these are what you have to write down in your mechanics, but let me show you how you get this. All right, so what we'll do is we'll enter these values in a matrix. So we enter these values in a matrix, and so we are going to go second x to the -1, right below the math button there where it says matrix, see that? Boom. And so we go edit matrix A. and we enter these numbers. And it's 3 by 2, just like that last one, 3 rows, 2 columns. And so we enter these numbers, 12 and 16 and 27 and 21 and 14 and 9, right like that. So right like that. I believe I got that right. Okay. And so then we just go stat, we go test, we go chi-squared test. Scroll down here. Not a goodness of fit. Goodness of fit is when you're using a list. Okay. All right. But we do chi-squared test like that. So A and B like that. Hit calculate. And there we go. There is our test statistic and our p-value and our degrees of freedom. Okay. And to see the expected counts, you have to write down the expected counts. Just go look at go edit matrix B is the easiest way. So go second matrix. And so we go edit matrix B, right like that. And so there's those numbers. Don't round to the nearest integer. Don't on expected counts. Your observed counts have to be integers. Your expected counts, they are integers sometimes. Most of the time they're not. So write those down right like that. And so then we do our p-value statement, just like we've been doing for several chapters now. This p-value is high, so we do not reject the null. There is not convincing evidence that, and then you restate the alternative. There is not convincing evidence that there is an association between level of the student and opinion on discipline. So that is what I read there. So there we go. That is how you do that. There's one more problem I wanted to show you. So that is chi-squared. And that is, I wanted to see if I could get you to notice there is a relationship when you have a 2 by 2 table. See, this wouldn't be, you couldn't do this if you had, a row or column number 3 or bigger. You couldn't do it on this. But if you have a 2 by 2 table, you have a choice, actually. You could do a chi-squared test of homogeneity, or in essence, association and independence, depending on how the problem's worded, or you could do a 2 proportion z-test. Because if you look at what happened here, it says, okay, a doctor wishes to know if there's a relationship in the patients who take drug A, or if there's a difference in the patients who take drug A and the patients who take drug B in regards to whether they experience nausea after they take the drug, shown below. I perform a chi-squared test, also perform a 2 proportion z-test. Okay, so when it's 2 by 2 like this, you have the option of a 2 proportion z-test or a chi-squared test. First of all, let's do the chi-squared test. Okay, so notice it talks about, is there a difference? And that's sort of this. Now, this wasn't explained really well. It was not explained that, this was, 2 samples or whatever, but it's the fact that it's asking, is there a difference between these 2 groups of people? That's saying chi-squared test of homogeneity. For it to be a test of association, it would have to say, is there a relationship or is there an association, between these 2 variables? So I'll go with homogeneity. The null hypothesis is that there's no difference in the 2 drugs in essence. All right, so, and the alternative is that there is a difference. We are told just to assume the conditions are met, so we can write that down. And so let's get our chi-squared test statistic. And so let's do that right quick. And so we will go second matrix and edit, and we will go matrix A, and it's a 2 by 2 matrix. And we'll just enter in these 4 numbers, 26 and 38 and 28 and 19. Like that. We'll do our chi-squared test stat, test, and go down to chi-squared test. There it is. A and B, boom, chi-squared test, test statistic, p-value, degrees of freedom. Okay, and so there they are. And so the p-value is below 0.05, so I reject it all. There's convincing evidence that there is a difference. There's convincing evidence that, in other words, that, and you restate the alternative. Well, what happens, the other way you could look at this problem is you could do a 2 proportion z-test where your proportions are the proportions of the patients that experience nausea. Okay, and you could also do it with a portion of patients that did not experience nausea, and you'd end up with the same conclusion. But so the way we're looking at our data is that, so our p hat for A is equal to, 26 experienced nausea out of the total of 64. Okay, and our p hat for our B, our sample value for our B, would be 28 out of that plus that is 47. And so the question here is there a statistically significant difference between this and this? And so we did this, a couple chapters ago, in essence. And so the null hypothesis is that there is no difference in these two proportions, similar to this over here. The alternative is that there is a difference. Okay. It didn't say anywhere up here where you go greater than or less than or anything like that. So then, our conditions are met here. And so now let's do our two proportion z-test. You remember how to do that? So you would go stat, you would go test, and we would do to the old two proportion z-test right there, option 6. And so we hit enter. And so we have 26 out of 64. And we have 28 out of 47. The alternative is not equal to, and we calculate, and look at that p-value. There's our test statistic p-value. The p-value is identical. It is identical. And the other thing, and so we would have the same conclusion. This p-value is less than 0.05, so I reject the null. There is convincing evidence that there is a difference between the two, just the same as this thing over here. The other thing to potentially notice that's not that important, but maybe a bit interesting, is the chi-square test statistic is exactly equal to the square of your z. So chi-squared is in essence taking your z test statistic and squaring it. Okay, so if you took your z test statistic, this number, and squared it, it's exactly equal to your chi-squared statistic. So anyway, all right, that's it. That is chi-squared. If you have any questions about all of that, I know that's kind of heavy, but you can get good at this. And if you have any questions, please let me know, and I'll be glad to chat with you. Hope you have a great day.